I thought I would talk more about the differences between algebra and analysis. So here we have graduate level algebra, and here we have graduate level analysis. So in an algebra course, I know I've already said this in a previous video, but I'll go through it again. Typically, you start with group theory, study those basic structures, and then this will take like an entire semester, and then in the next semester we talk about ring theory. And then we finish that semester with field theory. So I mentioned a little bit about what groups are. They're structures that have an operation defined on them such that they're closed under the operation and they satisfy three properties. The three properties are associativity, existence of identity element, and existence of unique inverses, I believe. And then ring theory throws in another operation on top of it, as well as some other axioms that you need to follow. And then field theory throws in multiplicative inverses, I believe. So a common example for rings are like the ring of integers, and then a common field as an example would be like the field of real numbers. Those are some examples of rings and fields. Whereas in analysis, it's a little bit more like the Wild West because it doesn't like stack on top of one another as much. They talk about a bunch of interrelated concepts, I guess. And the procedure, or not procedure, but what am I trying to say? The flow of the course is, it kind of depends on what the instructor wants to do. But usually there's a semester dedicated to measure theory. Can't really get away from measure theory. And then on top of that, you'll have metric and topological spaces. And that kind of sets the stage for the third thing, which is functional analysis. Oh, how do I describe these two classes, algebra and analysis? You can look up the definition on Wikipedia, but the way I interpret these two courses is that if I had to explain this to someone that doesn't have any mathematical background, I would say that algebra is the study of structures, symmetry, and patterns. It's all about identifying patterns. In many ways, I would say that algebra is the purest form of mathematics, which might be a backhanded compliment because you're kind of saying that there's no applications in algebra, so why bother with it? But that's not really true because there were two people that graduated from my program and got their PhDs in algebra, and they ended up going to work for the NSA. I never met these two people. I just heard, that's what they did after they graduated. So there are some good jobs out there in algebra that uses those algebra skills. Think about like cryptography and stuff like that. Or cryptology, not cryptography. I think cryptography is something else. So anyway, yeah, so that's kind of where algebra is at. Whereas analysis, if I had to describe it to someone, again, that doesn't have any math background, I would say that it is the generalization and, if I'm allowed to make up my own word, the abstractification of calculus. It's the theory behind calculus, in a way. So we talk about like what it really means to be a real number, what it really means to be a derivative, to be an integral, stuff like that. It's very complicated stuff. I don't have the best definitions. I just know the subject matter. And I think about it more that way rather than like, what does analysis really mean? What does algebra really mean? And yeah, so in general, I think that the way my brain works, I wanted to show you two ways of how problem solving works in both of these. So let's say that this is my problem in algebra. You're given some sort of hypothesis. which I call point A. And you need to prove something about it. So you need to make a conclusion, and we call that conclusion point B. And your job as the student is to figure out a path from point A to point B and write up that proof. And the process is in a very general way. This is not true 100% of the time. But this is like, if I had to draw a very simple picture, this is what it would look like. You would start and you would make some progress going forward, but then maybe you're led astray and then you hit this mark over here and you're not where you wanted to be. So then you go back over here to see, where you took a wrong turn, and then you start making forward progress, but then you get stuck again. So then you go back and say, okay, maybe I can try another way, and eventually you make it and you get to point B. So it's kind of a very direct way. I'm not saying that every algebra problem is proven directly, but if I had to describe the way I approach an algebra problem, this is kind of the approach I always take. I always start with point A, just try and do something based on what I know, and if I get down to a place where I don't know, I have to figure out where I took a wrong turn and figure out how to get from point B from there. That is how I would illustrate an algebra problem. In analysis, it's a little bit different story, and it's probably the reason why I struggled with analysis more than algebra. So in analysis, there's like a very clear path that you need to take, but then you get stuck. And you need to figure out how to unstuck yourself. And what analysts like to do is that they pretend they're at point B, and then they backtrack. And the goal is they need to backtrack until they eventually meet where they got stuck. And then once they find the place where they got stuck, then they just connect the dots and just pretend like they knew what they were doing the whole time. And then they get to point B. This is how I feel when I do an analysis problem. So there's the two pictures. It's funny that I demonstrate this because there is a woman in my graduate program, and I remember working on some analysis problems, and I was getting frustrated with them because I couldn't make any progress. And I had mentioned that I found algebra a lot easier, but I wanted to do my PhD in analysis, and she asked me. Well, then I told her this story. This is really the reason why I mention it. Is I told her a story about this guy that was in my analysis class, and I was frustrated a little bit about how much better at analysis he was than me because he was a kid. He was like 7 years younger than me, still an undergraduate. And he eventually graduated and got a job somewhere, probably making a lot of money. But he was very comfortable with analysis, but not so much algebra, which I thought was strange because I was the opposite. And she asked me if he was a domestic student or an international student. And I was curious. I was like, well, what do you... he was a domestic student, and I told her that. But I was confused by the question, like why she was asking. And she said that there's like a stereotype about domestic students versus international students. And I had never heard this stereotype before. And there may be some truth to it, but I don't really know. I don't have like a good sample size on it. And obviously with stereotypes, you have to be careful because not everyone fits into the stereotype. But here's what it is. The stereotype is that domestic students tend to be better at algebra, whereas international students tend to be better at analysis. But this guy was a domestic student, and he was way better at analysis than algebra. And I had a friend that was like that too. He was also a U.S. citizen. But there might be some truth to it because I noticed that in my algebra classes, the American students, like myself, were more comfortable with proofs like this. And one of my friends who's an international student, he was more adept at analysis, I think. At least when I asked him how he felt about algebra, he said he didn't like it. And that's kind of interesting. I mean, obviously my sample size is really small, and you take stereotypes with a grain of salt when you talk about stuff like this. But if I had to take a guess as to like why that phenomenon occurs, if it has some merit, I think it's because in US schools, there's a greater emphasis on algebra skills because it's what we've always done. Whereas in other countries that are still developing, well, I guess are politically correct. They're growing countries, we'll say. They tend to focus more on, I think they tend to focus more on analysis skills than algebra skills because they're more marketable. Let me know if that is the case, because I really don't know, because I haven't really been outside the US at all. But that, if I had to take a guess, that might be what's happening. But it doesn't really matter. I mean, we're still in the classes, still struggling together. So you can get an idea of what we're going through. Anyway, so now I thought I would show you two problems. Two problems from each. So I'm going to do an analysis problem and an algebra problem. Or two of each, I should say. So we'll start with algebra to demonstrate this picture in action. Now, you do probably need to know some of the lingo in order to follow along with me, but these problems, trust me, are simple problems. Okay, so what's the first problem? We have a group G, and we are given a normal subgroup. Again, you need to know what normal means, unfortunately. But normal basically means if I multiply on the left side of Gn, it's the same as multiplying on the right side of Gn, or of n. Again, you do need to know the terminology. And then we also assume that the index of n and g is equal to n, finite. And we want to prove the following statement. For any g in g, g to the n is an element of n. So that's the claim that we want to show. And here's how I prove it. Proof. I start here. Let G be given. And then I consider the coset. Consider the coset Gn. The reason I'm considering the coset is because I know something about this guy. Because the index is really the order of the quotient group. The order of the quotient group is n, which means that if I take my coset Gn and I raise it to the nth power, I know it's going to give me n. But Gn to the nth power is the same as Gn times a bunch of Gn's, such that there are n of them in terms. But I can rearrange this in a nice way. I can rearrange this as Gn n to the n, but that's just the same as Gnn. But because this is equal to this is enough to conclude that Gn gets absorbed by n. So I have Gn raised n to the n. Very short proof, especially if you know how to prove it. Unfortunately, if you don't know the words like normal and index and coset and blah, 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 then you get a little bit lost. If you've had some group theory before, this problem is pretty nice. So this was a very direct way of doing something. And I know I said I was going to do another group theory problem, but I don't want this video to go on too long, so I'm going to do one problem from analysis. I'm going to prove that the limit as x approaches 3 of 2x plus 4 is equal to 10. 10. This is an undergraduate level problem, and I think the reason I chose this problem is because I want to illustrate this guy in a very this is a perfect example of this, but it shows you just like how the two are related. I don't want to choose an analysis problem that's too hard. Okay, so how do you do it? Proof. We need to use the definition of limit. So it's again, you need to know what this definition is. The definition is this. For any epsilon greater than 0, we can find a delta positive such that for any x, in the domain, which my domain is R, if the following condition is met, so x minus 3 is less than delta, then if this is f of x, which we'll call this here f of x, then f of x minus 10 is less than epsilon. So this is what we need to show. So we start from the beginning. So here's part A. So let epsilon be given. And then we need to go forward. So going forward means we start here, we need to go this way. Unfortunately, we're already at this part here. Because now we need to pick this delta, but this delta is not obvious what to pick, at least at the moment. So now we need to go to part B and work our way backward. So part B is this dude right here. So now we're going this way. Okay, so what is it? So we have f of x minus 10. But what's f of x? F of x is 2x plus 4. And now we can play inside the inequality. So we end up with 2x minus 6. But we can factor a 2 out. So we get 2x minus 3. And we're saying that, and we want this to be less than epsilon. Wait, why did I write an epsilon here? Yeah, sometimes you end up writing your 3's backwards because epsilon looks like a backwards 3. And we want this to be true. So notice, if we divide by 2, we'll get this. And now our answer is staring us in the face. We want to define epsilon to be this guy. So if I was writing this proof up, this would be like off to the side. I would not include this in my proof. This is like the analysis step. So I would do this like on a separate sheet of paper. So I would start with let epsilon be given. And then I would pick the proof back up here and say choose delta equal to epsilon over 2. Then for any x in my real numbers. So now I figured out how to get here. Now I would say, okay, I've chosen my delta, then I make this statement, and now I need to say this. If x minus 3 is less than delta, which is equal to epsilon over 2, then that means that 2 times x minus 3 is less than epsilon, but that's the same as 2x minus 3, or 6 rather, is less than epsilon. But negative 6 can be rewritten as plus 4 minus 10, less than epsilon. And that's the same as f of x minus 10, less than epsilon. So you can see here that had I skipped this meat inside and just went straight here, this feels like it just comes out of thin air. Like, why on earth would you want to rewrite negative 6 like this? How on earth would you choose this epsilon 2? And the trick is that you don't. You start at the end and work your way backward to figure out what steps you need to take to get there, which is what this is. So I would write this, move this off to the side, and then pick up this back here after I figured out what I needed to choose my delta as. So this is a really good example of a problem in analysis. Anyway, so that's algebra and that's analysis. Which one do you prefer? I tend to prefer analysis because I think it's more difficult for me and I like to push myself, I guess. Algebra, that's not to say algebra isn't easy. It's definitely not easy. There's some really pathological algebra problems out there that I don't want anything to do with. It's just I find analysis a little bit more meaningful to me because I feel like it's the thing that I need to do. I wish I could explain that better, but some things just speak to you and other things don't. But personally, I kind of was in the position where I wanted to learn everything, but I ended up settling with analysis because I felt like it was the thing I needed to do. Let me know what you think. Let me know what subjects in math you prefer and what you want to get your PhD in, because I'm interested in hearing. Why did you choose your respective field? Anyway, thanks for watching.